with Mr. Huang, who's working for the State Grid Corporation of China. He is currently the Deputy Chief Engineer of the State Grid, as well as the Director of Northeast Branch. He's a Doctor of EE and the professor level Senior Engineer. So with that, I'll welcome you to the stage.
Good afternoon, the honorable specialists and the colleagues. It is my pleasure to share with you the integration of high levels of new energy in China's Northeast Power Grid of State Grid Corporation of China. My report is divided into 3 parts: background, overview, and practices. The first part is background. In June 2014, China put forward its new strategy of energy development, which is 4 revolutions and 1 cooperation. In September 2020, China proposed its goal of carbon peaking or carbon neutrality, striving to achieve carbon peaking by 2030 and carbon neutrality by 2060. In July 2023, China announced to accelerate its construction of new power system. The second part is overview. SGCC consists of 6 major regional grids. China is the country with the fastest growing and the largest scale installed capacity of new energy in the world. By the end of 2024, the total installed capacity of power sources of SGCC had reached 2.63 terawatts, of which the installed capacity of new energy had reached 1.14 terawatts, accounting for 43.3%. Northeast Grid is one of the 6 major regional grids of SGCC. It serves area of 1.28 million square kilometers and a population of 106 million. Its installed capacity totals up to 232 gigawatts, with its power generation reaching 642 terawatt-hours in 2024. Its max power load reaches 82.32 gigawatts, and the electricity consumption reached 570.8 terawatt-hours in 2024. China is the country with the fastest growing, From 2021 to 2024, the installed capacity of new energy has doubled, exceeding 100 gigawatts, accounting for 44% of the total installed capacity. The high-speed development of new energy also brings problems to grid operation, which mainly involve 2 aspects. One is the difficulty in power system balance. The contradiction between insufficient supply and excess supplies of new energy is prominent, and the arrangement of conventional power sources is becoming increasingly difficult. The other is the stability problem of power system. Power generation from new energy sources takes up as high as 58.6% of the total. The natures of new energy sources, such as low inertia, low damping, and weak voltage support, appear obvious. In this case, how to keep frequency and voltage stable becomes increasingly complex, and the risk of chain reactions failure is continuously increasing. The third part is practices. Northeast Grid carried out planting of creative practices in respect of mechanism, management, and technology. In terms of building a strong interconnected grid, provincial aid in Northeast Grid, 500 kilowatt provincial AC transmission lines and plus and minus 500 kilowatt DC power transmission projects were built, making its trans-provincial mutual and capacity reach 31.2 gigawatt, nearly 40% of its max power load. In 2024, the electricity quantity under trans-provincial mutual aid reached 101 terawatt-hour. Interregional delivery, a plus minus 800 kilowatt UHV DC transmission line was built, which delivers electricity to North China Grid with a rated capacity of 10 gigawatt. A back-to-back DC power transmission project was built to deliver electricity to North China Grid with a rated capacity of 3 gigawatt. In 2024, its interregional power delivery capacity reached 10.5 gigawatt, electrical quantity to 64.8 terawatt-hour. Improving grid security performance. To deal with the shortcomings of new energy, we spent 3 years upgrading the whole grid for higher withstanding capacities of new energy. After upgrading, the frequency tolerance capacity reaches plus minus 1.5 Hertz, basically same to the conventional power sources. Exploring the applications of new technologies, we carried out performance tests on a 50 megawatt static synchronous compensator and new type of storage with a capacity of 15 megawatt. An artificial short circuit test was performed to verify the voltage and the initial support capacity of the grid forming equipment, which can be reached 3 times capacity of a grid forming device. Resisting high frequency risk, we built a higher frequency emergency control system to control the power capacity at a level over 17 gigawatt. The system rapidly cut off the supplies within 200 milliseconds, ensuring the fluctuations of frequency in the range. Resisting, sorry. We built a low frequency emergency control system with controllable resources exceeding 14 gigawatt. Enhancing the regulating capacity of coal power by upgrading the combined heat and power generation of coal power units. Through market incentive mechanism, we have improved the efficiency and the peaking capacity of coal power units remarkably, while increasing residential heating. By the end of 2024, we had completed the upgrading of 16 gigawatt coal power units. During periods of significant power output of new energy, the average load rate of coal power dropped down to 34%, while some units even dropped down to 14%. Accelerating the construction of pumped storage. There are 5 pumped storage stations in operation, with a total installed capacity of 5.9 gigawatt. There are 9 pumped storage stations under construction, with a total installed capacity of 11.7 gigawatt. Promoting new type energy storage applications. There are 68 new type energy storage stations in operation, with an installed capacity totaling 2.58 gigawatt. By the end of 2030, the total installed capacity will reach 25 gigawatt. Compared to 2021, the annual power generation of new energy doubled in 2024, rising from 91.5 to 188.6 terawatt-hour, with a percentage of from 17% to 29%. By 2030, the installed capacity of new energy will reach 260 gigawatt, accounting for 60% of the total installed capacity. That's all. Thank you.
Up next, we have Mark from Xcel, who's going to kind of walk through their plans and their integrated resource plan. And I guess in the first session, I heard a lot about language and, how we say things and what we're saying. Integrated system planning is quite dynamic, and there's integrated resource planning, there's resource stacking, and really the phenomena behind resource system planning is gathering the right stakeholders in the right rooms and really discussing what is needed all the way down to execution. So it involves policy, regulatory making, but also planning, operations, and all of the coordinating individual units within a utility. So I look forward to hearing each one of our next panelists' perspectives. And then after they present, we'll jump into some Q&A. Okay, with that, Mark.
Thank you, Liz. I'm a little disappointed you chickened out on saying the last name. It's Schoenheider. It's not that hard. You wouldn't be the first to have messed it up. So Good afternoon, everybody. Mark Schoenheider with Xcel Energy. Before I dive too far into the weeds, I want to tell you a little bit about Xcel. For those that don't know, we are an integrated electric and gas utility. We have distribution, generation, transmission, as well as gas service in parts of 8 states. Total of ballpark 5 million gas and electric customers. Most of my discussion today is going to focus on Colorado, which is one of our states. It's where I happen to live. In Colorado, we have about 1.5 million electric customers, about 1 million gas customers, and our current system summer coincident peak load is about 7.5 gigawatts. So nothing on the scale of what you just heard, but it is our system. So we're going to talk about the grid of the future. And oops, let me go back one. At a high level, the grid of the future is really a journey for us. And it's a journey from top down, sort of individual planning at the distribution level, transmission level, generation level, gas side, to bring it all together. It's a journey because we're not done, right? We took some monumental steps, and we'll talk about some of the work that went into it. We'll talk about some of the results. But know that there's a lot more. There are many, many things that as we were going through, we either didn't have the time, the resources, or frankly, the tools to do kind of the way we ideally would have liked to do it. But we have ideas of where we need to focus for the next round. So with that, why do we need to do things differently? So I think everybody in the room is some way, shape, or form involved in an electric utility or worked with an electric utility, or maybe is just a customer of electric utility. This is the sort of high level transition of the utility industry through the ages. And I'm going to focus on really the last 2 columns, the power sector decarbonization and then economy-wide decarbonization and growth. And I'm going to do that because that's really that the second from the left, or sorry, second from the right is what set us up for the need to redo this and to redo how we plan. And that is that from roughly 2010 through today, our electric utilities and really focused in Colorado, but true of all of our 8 states, have gone through a process of decarbonizing our electric generation. And we have been able to do that largely with very little to no notice of the customer, right? They don't really see it. They don't know what's going on. They turn on the light switch, lights still come on. Their bill has remained remarkably flat over this time period, while we have reduced about 50% of the carbon from our generation assets, right? And we are very fortunate across our operating companies to have great solar and wind resources. So it's been pretty easy for us. Easy. The next stage, though, economy-wide decarbonization, has really been driven on the power sector decarbonization, where specifically in Colorado, our legislatures and regulators have understood that, hey, if you can clean up electricity, which you have, and you have a plan to get to 80% carbon-free by 2030 and 100% carbon-free by 2050, we can now use electricity to decarbonize everything else, right? Whether that's industrial processes or the much more sort of relevant to individual customers of transportation, space heating, and water heating. And so we know and see that coming. The question is, what are we going to do about it? We have historically at Xcel done what I would call top-down planning, right? We have a load forecast, we have a customer growth forecast, we kind of see the trajectory of the bulk system load, and we say, okay, this is what it's going to look like. Given the changing environment with what you see in the second column, a whole bunch of different customer adoption vectors from transportation, cooling, heating, and then the bottom one are like batteries, energy efficiency, solar. Those traditional load curves for individual customers and then aggregate up to distribution assets, transmission generation, those are all changing, right? And the question is, how are they going to change? And so the graphic you see here represents our pathway through our grid of the future modeling. And super high level on the left side, one thing we're doing differently is we're not just planning to a specific scenario, right? Because we have different environmental goals in the state. We have different likelihoods or propensities for customers to adopt. And, you know, there are macro level things that change that, right? Whether it's presidential administrations, whether it's economics of the day, whatever, we don't know. Anybody raise your hand if you can predict the adoption rate of electric vehicles in the next 10 years. Exactly, right? The only thing we know about any of those forecasts is every single one of them is wrong. So we added multiple scenarios. We'll talk a little bit about the scenarios and the customer adoption vectors in a minute. The key in that third column, though, is we literally started with a forecast of energy consumption hourly at every single premise, and then aggregated that up to understand for every single one of our feeders, every single one of our banks, every single one of our transformers, where we would have capacity constraints, right? Where we expected them to happen, how long they were happening in a given year, and the magnitude of those, which then led us to, okay, let's identify different projects that we would need to do to mitigate those, which, I mean, that's all fairly traditional distribution planning, with the exception that it was kind of flipped on its head. Instead of being top down, it was literally started at every premise. We were then able to take that and sort of level it up to transmission. Okay, if we have these new substations, what does it mean for transmission needs, and what does it mean for resource needs on the generation side? Because again, as we're adding all this load, we also have an ever increasing mandate on our electric generation to be basically carbon free by 2050. And so how many of you have dispatchable wind and solar? No, right? So we have to account for that and understand what other components need to be in that mix. On the right side, the output, there's quite a few different audiences for the output. You know, our investors are very interested in our investment envelope. Our regulators, as well as everybody at Xcel, is very interested in the impacts, the financial impacts to customer. And then we have all of the system planners and design engineers that, as we heard about, if you're in this room earlier today, one of the key themes was, are these things dependable? What's going to happen if, you know, customer behavior doesn't follow what we thought? So, okay, I'm going to dive a little bit into the different scenarios we modeled across the top. We have our first scenario was basically calibrating against our current distribution system plan. And that is, in a lot of ways, that's a very well engineered. Every single risk on the system has a mitigation design, costed out, you know, very thoroughly engineered. And that scenario, we'll talk about the adoption vectors in a minute. It basically says these are all of the customer adoption vectors for things like electric vehicles, rooftop solar, community solar gardens, heat pumps, that we've already agreed to, or already are in active sort of plans with our customers. So we have a transportation electrification plan, we have a clean heat plan, we have a demand side management plan. The next column over, the policy one, is, okay, let's look a little further out and say, for all of the laws that are currently on the books, what would have to come true for those to make sense? The third one, the goals, is the state of Colorado specifically has what they call a greenhouse gas pollution prevention roadmap. It basically goes industry-wide, sector by sector, and says these are the levels of reductions in emissions you have to meet by a certain time. It has nothing to do with how those will happen. It just says these are what you have to get to. And so we modeled that scenario. And then the farthest to the right is really kind of, if you sat back and looked at what actual adoption looks like for these various technologies, it's kind of what we think will happen, right? And it may surprise some, it may not, but that one in a lot of cases had lower adoption rates than maybe what the state policy goals have. But in some cases, it actually had higher adoption rates. So, okay, these are the different demand vectors we modeled, light, medium duty, and heavy duty EVs. We further broke those out into like residential versus public charging versus fleet. And then on both residential and commercial, we had space heating and water heating. And then on the right-hand side, there's a lot of behind the meter, either solar or storage, energy efficiencies in there, as well as demand response, both on residential and commercial side. Okay, this picture was meant to be a very simple picture to give stakeholders and regulators an idea of what we're doing. It ended up raising a lot of questions. I will start by saying, no, we don't expect that every customer will look like that customer on the right. But at a high level, the left side current customer gives a high level overview of what kind of our average customer looks like. They have an air conditioner, they have a gas water heater, they have a internal combustion engine vehicle. Their cooking and laundry is sort of a split between electric and gas. On average, they peak in the summer 2 to 6 p.m. on a hot weekday at about 5-ish kW, somewhere in that ballpark. And throughout a year, they use about a little over 7,000 kilowatt hours. On the right is sort of this low carbon customer of the future. They are pretty much electric everything. You'll notice their annual kilowatt hours go up to about 17,000, so a pretty large reduction. There are corresponding reductions in natural gas usage and gasoline usage. And then the other key here is their peak demand. So non-coincident peak, but within the customer is somewhere around 16 kW. Now, if you just added up the nameplate loads of everything, all of their electric appliances, it would not equal 16. It would be way, way more than that, right? They may have 16 kW in heating alone in our Denver climate that gets down to 25 below zero. But this is not every EV charging at the same time, water heater running, cooking, space heating, everything at the same time. It's really it is their peak. Super high level, and this is probably fairly hard to read. This gives a bit of an understanding. So our system today, the key number here is we have about 800 feeders. By 2030, we'll have roughly 300 more than that. And by 2050, we'll be 2.5 times that size. That's a ton of construction, a ton of, and there's a whole lot of load management and demand aggregation built into this. Other numbers in here right now in Colorado, I think as of the end of December, we actually have about 143,000 EVs on the road. It will be 3 million. We have close to 10,000 heat pumps now between heat pumps and heat pump water heaters. And by 2050, in the calibration scenario, we're at about 2 million, split about half and half between heat pump water heaters and space heating heat pumps. Okay, probably the most important slide, 2 slides. I have one that is, this is the costs, and this is effectively an average customer's bill for energy, right? And so the top line is 2025. If you see $3,300 roughly in gasoline, a little under $1,100 in electricity, and a little over $800 in natural gas. The bottom 3 lines they don't represent any individual customer. We sort of looked at it as these are all 2050. The top one is a customer that's sort of in the 90th percentile for decarbonizing their life. The third line there, that average customer is sort of 50th percentile. They do some things, they don't do other. And then that bottom customer is really, it's, no, I'm not up for this. I'm just going to continue doing what I'm doing, right? And there is some efficiency baked in. But generally speaking, they are sort of a no action. They kind of are that 10th percentile of doing nothing. The good news on the slide, though, is when taking into account long-term rate forecasts for both gas, electricity, as well as all the other things baked into life, whether it's mile per gallon on vehicle improvements on the gas side or the electric side, the takeaway from this slide is what we have come to understand is our average customer will actually spend a lower amount of their income than they do today, right? And even that do nothing customer, that no action customer, is going to spend a little bit less on energy. And the funny thing, or I don't know if it's funny or not, maybe it's common sense, is that low carbon customer is going to be somewhere in between those two. So you might say, if we're doing a lot of this for carbon, what are the carbon implications? This is the same setup for the slide. The customer today has a little under 16,000 kilograms of carbon emissions today. Even under the no action, do nothing, you cut about 35% of that out. And so that's largely due to the continued electrification or the continued decarbonization of the electric grid. But then when you look at the average customer and the low carbon customer, they get significantly better, right? And so that low carbon customer is using less than 10% of the carbon that they are using today. And even the average customer has reduced their carbon by about 80%. So I think that is it.
With 10 seconds to spare. Next up is Aaron. I just wanted to point out 2 observations. Our first presentation was very top-down planning and execution, 5 work streams, right? It was the bulk generation, transforming it to a new energy source while building out transmission, while retrofitting and transforming existing infrastructure with old energy sources, as well as the pump storage and the energy storage. So there wasn't a one solution. It was, they actively were pursuing 5 solutions at once and integrating all of those together. And then what you just summarized was a lot of the from the bottom up perspective and really the details needed from a distribution and the customer level and how can that triculate to the top to create a capacity margin. Anyway, I just wanted to point out, and I think it's really interesting and something to think about when we hear the rest of the plans of how important it is not to lean into one silo and understand how integrated this must be and action must be taken and learn from those actions. So here you go, Aaron.
Okay, hello everyone. Good afternoon. Aaron Burdick, Director at E3 in the Integrated System Planning Group, and that's what I'll be talking about today, our work on integrated system planning at E3 and with ESIG. So I think most folks know about E3. We're a technical consulting firm, about 130 consultants, 5 offices across North America now. But I wanted to start with some of our work that we've done on this topic so far. So we had the privilege of supporting some of the inaugural integrated planning efforts at Hawaiian Electric and the Salt River Project, have continued that work with utilities, as well as work with regulators in California, Illinois, and more recently, we started a project in British Columbia looking at integrated gas and electric system planning. We've also done our best to contribute to the thought leadership in this space. So we had a webinar series and a white paper release last fall. And then since then have been working with ESIG, leading the Integrated Planning Task Force. So I'd like to just highlight, oh, my slides got messed up here. Oh, well. Some of the forthcoming white papers from that task force. So the first will be called Foundations of Integrated Planning. This will be focused on what are the core components of a holistic planning framework. The second will be a guidebook, which Carlo will be talking about shortly. And then the third is a paper on optimization for integrated planning. Basically, what are some of the opportunities and limits for using capacity expansion tools historically used on generation planning to do more integrated analysis. And that's what will be the core of my talk today. So a bit of background. So why do we need integrated system planning? I'm sure it's obvious to everyone here, but I'll just go over a few points. So on the left, you have all of the drivers that we've been discussing at this conference. You have decarbonization policies, new types of load growth, data centers, electrification amidst new climate risks, and aging infrastructure. So Mark threw out the $1 trillion number. Some of the studies that I had seen are the energy transition in the US could cost multiples of that, maybe $3 to $6 trillion over the next 25 to 30 years. So this is a huge investment. We need to ensure that those investments allow us to maintain a reliable, affordable, and increasingly clean grid. And the way to do that is to have planning processes that can help us identify the right types of investments in the right locations at the right times. And when we look at the traditional electricity planning processes, you can categorize them into categories: generation, transmission, distribution, and customers and DERs. Those have historically been generally siloed. So each has their own set of models, their own people, their own conferences, their own vocabularies. And that has mostly worked fine. And one reason it's worked fine is that historically, when you made investments in one planning domain, they had limited impact on your needs in other planning domains. This is no longer the case. So we can take the example of building a battery storage resource to prove this point. So maybe you have a generation adequacy need that's driving that storage resource, and you can cite that on the bulk transmission system. You can cite it on the wholesale distribution side or behind the customer meter. Those all could serve different purposes and potentially multiple purposes, depending on where that asset is placed. So moving to an integrated planning model focuses on holistic planning that can link these traditionally siloed processes to achieve the same outcomes, affordable, reliable, and robust investment plans, and hopefully do so with more efficiency, ultimately leading to lower cost outcomes. So before I get into some of the analytical processes, I want to say there's no one-size-fits-all approach. So you can understand that planning is going to look much different in northeastern China versus Hawaii versus New England or Texas. We have such a variety of regulatory models, and that means that integrated planning is going to look different in different places. But the key is really focusing on what are the right data linkages between these historical silos so that you can come to that holistic solution. So I'll give everyone a tour here through all of the integrated planning data sets that we think need to be connected. So we can start by laying that out in these three categories. So the first is developing the inputs to planning that will determine our system needs. So that's really driven by the load forecast and DER forecasts. Those need to get downscaled so that they're consistent but applied at different granularities for generation planning, transmission planning, and then feeder level distribution planning. You have your resource auction study that's historically been a part of your IRP process, where you're looking at bulk grid resource solutions that increasingly may consider DER solutions, as well as potentially grid upgrades as candidates that you want your planning process to be able to select from. Then you have your adequacy study that determines your generation capacity needs. There'll be lots more arrows coming soon, and there'll be a quiz on this at the end, so pay attention. So then you have your generation capacity expansion that takes all that information and produces an optimal portfolio over 20, 25 years into the future. That optimal portfolio can be run through production cost modeling at the zonal or nodal level. That supports both validation of the expansion plan as well as operational planning and transmission planning when you get into where resources are located and where the grid might be require expansion to address congestion. You may have a feedback between those transmission studies where you're looking at that portfolio and how it actually operates with a more detailed representation of grid physics. So that could determine additional ancillary service needs or dispatch limits that would feed back into some of those generation planning models. And you have all of your detailed grid physics, power flow, contingency, stability, all of those analyses within the transmission planning process. There's a coordination about the topology of the T&D interface, and then you have your distribution studies that are using those granular load and DER forecasts that got produced. And those feed into what your grid needs are, and there may be an assessment of whether those grid needs can be met with alternative solutions like distribution deferral by DERs, what we call non-wires alternatives. And then you have customer programs and DER planning. So this could include forecasting, it could include customer program design, can also include rate design. And all of that needs information from your other planning processes about what the costs that can be avoided by local DERs are on the bulk grid, on the generation side, transmission side, and potentially the distribution system as well. Then you have a feedback from some of those DER planning processes into forecasts that you'll use to inform your next planning cycle. So really simple, right? So, the question is, that's a very complicated process. There's a lot of data linkages that you may need to capture to really do integrated planning right. And so can't we just put it all into a single optimization model? We all love optimization models. They make our lives easier. And the answer that we at E3 think, and most folks on the task force have also agreed with, is no, you can't do that. You can't have a single model that optimizes everything, partly because of the just data and computational limitations, and partly because we're starting, when we start with capacity expansion, with an economic modeling framework, and that just has limitations for the amount of the physics that you can capture there that's really required to do all of the grid planning. And so we see this set of multiple coordinated processes to facilitate integrated planning as the scalable model. But then the question is, well, if you can't optimize everything, can you optimize more than we optimize today? So that's what I'd like to talk about next. So when we think about the benefits and challenges of co-optimization, if you can endogenously identify those holistic investments, of course, there's a benefit to doing that. You can understand where to build out your transmission grid while you're looking at the generation that would be interconnected. You can figure out where to optimally site energy storage. You can balance how much investments you should be making in bulk grid resources versus DER resources. And all of that should allow for a lower total cost solution with fewer iterations between your planning processes. Now, of course, to do such a larger optimization problem requires a lot more data, requires producing more data, and generally more granular data on the locations of loads and resources. It comes with the potential for false precision or over-optimization. So you might optimize yourself into a solution that may not actually be implementable in the real world. And just the larger problem size poses tractability challenges. And as I'll talk about shortly, you can't fully eliminate some of those iterative processes with more detail on the physics. So when we think about expanding the capacity expansion optimization problem, we have to understand that we're already making major trade-offs to be able to solve just the generation system. And those trade-offs I've categorized them into 5 different categories here. So you have spatial granularity, temporal granularity, operational detail, grid physics, and resource options. And generally, capacity expansion focuses on the resource options. You want to have a broad solution space for the model to explore, look at lots of different scenarios, and it has simplifications of some of the other dimensions that are captured in more detail in other models. So it is often at a zonal or more aggregated level. Spatially, you have representative days or weeks, approximations of commitment and dispatch, and so on. When we think about integrated planning, specifically the 3 shown there, spatial granularity, resource options, and grid physics, we would need to expand the representation of those within the optimization to do more integrated analysis. So let's start with the easier problem, which is G&T co-optimization. So there's a variety of models here, and I'm going to walk through some of them. And we can think about these in this table. I have 2 rows. One is the granularity of the capacity expansion dispatch, and the other is the representation of the transmission system and its constraints. So you can have a one-way flow. That's the first column. That's really no integration. So you make your generation portfolio and you study its transmission limits, but there's no feedback. You can have an iterative process that provides feedback between your G&T planning processes, but that's inefficient to go and change your generation solution without representation of any of the transmission limits in the expansion. And so the blue and the green categories on the right show representing the transmission grid in the expansion. So in blue, you have still a more aggregate zonal dispatch, but you can have the transmission constraints represented either at the resource level or at a transmission zone level. A transmission zone level, like the RES or CRES type of approach, allows you to capture some of the diversity in siting, let's say, solar and storage together to maximize new line utilization. And then on the right, you have pipe and bubble representation. So this has a variety of flavors. You can look at BA to BA, zonal upgrades. You can look all the way down to the nodal level, doing nodal dispatch and nodal transmission representation. That's a lot more data that can pose computational challenges. And so the aggregation of nodes into zones within your investment zone is sort of a middle way there to capture some of that detail. And as I mentioned, there are some limits to what you can do in an economic model. So you still want to run DC power flow, AC power flow, contingency stability, these other downstream processes that capture the grid physics better. Those can both validate the combined G&T co-optimized outcome, and they can also identify additional constraints or upgrades. As I mentioned, some of those constraints can feed back. So you still might have some iteration between these models and a co-optimized G&T process. Okay, so now thinking about that, taking that bulk grid co-optimization and trying to assess how much of the DERs and distribution planning we can fit into that. And you can certainly see the appeal when you think about the fact that DERs are in part driven in their cost effectiveness based on the bulk grid investments that they can avoid in generation and transmission, and how many resources you want to build on the bulk grid versus local grids is a function in part of the additional value that you can get from having resources on the distribution system. I will say the key challenge in doing this full system co-optimization is really characterization of the distribution constraints and deferral opportunities with enough granularity at this system level optimization. So we can think about that if we think about going from a zonal representation on down. So if you just have one zone, then you have one system with its resources and you have one load forecast. If you want to break that into multiple transmission zones, maybe a few or over 10 or 10 to 20 different transmission zones, that means you need 10 to 20 resource forecasts and load forecasts. And if you try to apply that all the way down to the distribution feeder level, you get to hundreds or thousands of different distribution feeders, each with their own load forecast. So, this is generally intractable within a system-wide optimization to have that level of detail to capture load resource balance all the way down to the distribution feeders. So then the question is, can you make some sort of trade-off that gets you enough representation to be useful, even if you can't have that high level of precision? So, the thousands of distribution feeders is kind of option 3 here. It's intractable, but it precisely measures local value. On the left, you have a system average. So this is called a peanut buttering from some folks of avoided distribution value. So it's easier to run in the models, but it doesn't really give you enough locational value to really be bankable as to how much you want to build on the bulk versus local grids. And then the T&D interface, there's a whole spectrum kind of in between here that trades off, computational tractability with how precise of a measurement you can get. And then there are some other methods that folks are exploring that might be good enough, like grouping your circuits into archetypes or CRES style limits, looking at distribution constraints. But no one has really cracked this nut to be able to capture precise locational value in this system-wide optimization. So a few thoughts on alternative approaches. So I don't want to leave you with the downer that you can't do this type of integrated planning. There are other alternatives to be explored that can capture all of the 4 planning domains. So the 2 I'll show today are largely based on the avoided cost model. So this is similar to how California does planning for generation, transmission, and DERs. So you have a capacity expansion that does co-optimize generation and transmission. Maybe you optimize some DERs on top of your forecast. That produces a resource portfolio that you can run through production cost modeling to get your avoided costs for energy and ancillary services. You can also get avoided costs for capacity and policy constraints like clean energy or GHG reduction. And then you can develop through transmission and distribution planning studies as granular avoided grid investment costs as you want. And how granular you want to go will really depend on how you're going to actually use that information in your sourcing. So you can put all of that into an hourly avoided cost model that allows you to consider what the value is of different DERs. It allows you to forecast adoption of different DERs, and it can also inform rate design for tariffs that might incent DER adoption. The second alternative, and just about done here, I got the poke from Liz, is instead of trying to take all of those thousands of small systems and put them into a single system-wide optimization, you can take the results of your system-wide optimization into a bunch of local grid optimization processes. So you can take your bulk grid avoided costs and apply those in an integrated distribution system framework, looking at DERs versus distribution investments, subtracting the bulk grid value from the DERs. And with that, I will hand it off. Thanks very much.
Good afternoon, everyone. My name is Carlo Brancucci. I'm the CEO of encoord. It's a pleasure to be here. Thank you, Debbie, Isaac, Liz, for the invitation. We've been hearing from our previous presenters about different approaches for integrated planning and also about the need for integrated planning across the electric vertical, from generation to transmission to distribution to customer planning. However, there is, like Aaron mentioned, many ways to integrate traditionally siloed planning processes. And depending on the regulatory reality, depending on the characteristics of the power system, depending maybe on the country that your power system is powering. And what we found is there is a lack of a definition or description of how to integrate planning processes across the electric vertical. So we have partnered with ISIG last year to address this very specific question. What does it mean to do integrated planning in practice? So in order to answer this question, we have joined ISIG's Integrated Planning Task Force to develop the Integrated Planning Guidebook. What is the guidebook? The guidebook is a practical guide for any planner in any planning area, generation, transmission, distribution, or customer and DER programs at any stage of integration. And it is meant to provide a practical reference on how to do integrated planning at different stages of integration and for different needs of integration. It is a single reference document. What it means is we have consistent terminology and structured integrated planning processes across any interface. So across generation and transmission planning, or across transmission and distribution planning, or across generation and DR and other customer program plans. The most important value of this guidebook is this guidebook was not developed by me and my colleagues. It's developed in conjunction with the Integrated Planning Task Force of ISIG. So it's been informed, reviewed, and will ultimately be approved by a task force of planning experts, primarily from the United States, but they include definitely experts from other countries across system operators, utilities, national labs, software vendors, and consulting shops. And they've been extremely helpful in helping us understand not just the need for integrated planning, but the challenges of integrated planning, as well as practical examples of how different system operators and utilities have already been implementing and thinking about integrated planning. The guidebook is not just informed by the task force itself, but also by interviews with industry experts, as well as by literature review of research papers by EPRI, NREL, and others, but also by planning filings from different utilities in the US and other parts of the world. So the guidebook starts by providing an overview of power system planning. So the guidebook will define different dimensions across every planning area in a consistent way. So it will define the scope of every planning area in terms of what are the objectives of a given plan and what are the boundaries of that plan. The scale, so what is the level of detail that plan covers? Is it a national plan, or is it a plan for the distribution system of a specific territory or a specific city? What is the horizon of the plan? Are you planning generation for the next 30 years, or are you planning distribution infrastructure upgrades for the next 3 years? And then what actions are being informed by this plan? Are you planning transmission infrastructure upgrades, or are you planning investments in energy storage at the bulk power system? We apply the definition of scope, scale, horizon, and action across generation, transmission, and distribution and customer planning areas. The purpose of doing that is to allow any planner to really learn about the planning of the other planners in their organization. Every presentation I've heard about integrated planning, not just at ISIG, but in any other venue, they have one thing in common. The number one challenge of integrated planning is people, is being able to work with people that think differently than you, that speak probably a different language, technically and not technically in some cases, and also people that are planning for very different needs and with a very different scope, for different geographies, for different horizons. Understanding that is the first step in integrating planning, in coordinating any process with someone that may be planning for a very different horizon than you, or that may be planning for a very different scale, physical scale than you, but that interacts with you. And ultimately, the reason why do we need to do all of that is because whatever a generation planner does is going to end up impacting the transmission distribution planners and vice versa. And Aaron gave a very good overview of the needs of integrated planning. What the guidebook also provides is it applies these dimensions of planning, not just to the individual planning areas, but the modeling domains or modeling approaches used within each planning area. So it provides details about the scope, the horizon, the scale, the actions driven by capacity expansion modeling done by a generation planner, or when running balanced power flow simulations by a transmission planner, and so on. Obviously, I don't have details to go over this, but what I want to highlight is that the guidebook allows planners to really understand how maybe the models they use in their planning process can interact with other modeling tools in other planning areas, but more importantly, what are the challenges as well as the opportunities to integrate the inputs and outputs and align them between all these modeling domains that may overlap in terms of the physics of the system or in terms of the economic operation of the system. The Integrated Planning Task Force has been extremely helpful in coming up with an agreed list of new challenges or change drivers for integrated planning. And those range from, rapidly changing policies that we are clearly experiencing at the moment, large uncertain load growth that we're also, it's definitely a big topic. I mean, it's the center of this event this week. The complexity of value stacking of technologies that provide a lot of different values that affect the planning, that affect across all planning domains, like energy storage, for example. What is key is all these challenges affect all planning areas. And understanding how large and uncertain load growth, if I'm a generation planner, understanding how load growth is going to impact transmission and distribution planning is extremely helpful for me to understand how do I integrate my process with theirs. So the whole purpose of the guidebook with respect to the challenges is provide examples of how these change drivers are impacting the different planning areas in very different ways. Then the core of the guidebook is an integrated planning framework that is broken out in 3 stages of integration: walk, jog, and run. And these are different phases of integration that build on one another and are meant to meet planners that see a need or have been requested to integrate their planning processes where they are. The walk phase is based on building trust between them and enabling communication channels so they can first understand each other. So I'm going to walk you through this walk, jog, run framework using one interface example, and I chose generation and transmission. But the same will apply for any other interface. So in the walk phase between a generation and transmission planner, the first thing is to understand, as a generation planner, what do I need to know about transmission planning? And as a transmission planner, what do I really need to understand about generation planning? And examples are, for example, if I'm a transmission planner, I may want to understand the type of modeling abstractions I do in resource planning models that I may not be used in my physical models. Or if I'm a generation planner, I may need to understand the physical realities of a transmission planner that I'm not used to consider in my generation plans. The next phase of integration is the jog phase, which is focused on aligning data inputs. So developing processes to allow, in this case, a generation and transmission planner to align common inputs. For example, every generation planning model and every transmission planning model has every generator in the system in their models, but often they're not represented in the same way or in consistent ways, or they even have different IDs that represent them. So how can they map their generation, for example, data between them? And that's not just across generation, that in a nodal resource planning model, you're going to have the whole transmission representation. How do you map demand in your generation model with respect to your transmission model? And then another example will be generation planners plan for 8760 hours of the year generally, while transmission planners plan usually for steady state peak demand periods. So how can they develop a process where transmission planners have access to the hourly operational, let's say, envelope that a generation planner is planning for, so that they can evaluate other potential at-risk periods beyond peak demand periods? How can they build a process to transfer that information in a seamless way and in a way that they can trust? Going back to the walk phase, it's about trust. It's about trusting why the other planner is doing what it's doing and why it matters and why does it affect you. The third phase is the run phase. The run phase is based on developing iterative modeling workflows. Aaron introduced that before, how a super optimization model that takes care of everything is intractable. There are a lot of ways that you can enhance your optimization models to capture some details and needs beyond, what is traditionally considered in a resource planning model. But there is a lot of physical realities and a lot of planning that dimensions beyond resource planning that require that iterative process. This guidebook focuses in the run phase in detailing example practical workflows that different planners can establish to integrate their processes. So I'm gonna give you an overview of what that means for generation and transmission. So the first thing is you wanna define a base case strategy. So you're gonna define a state of your system, and you're gonna define one, ideally multiple mitigation strategies. So you expect large demand, you expect, you have aging assets, new technologies, et cetera. You need to make different investments in generation and transmission. How do you coordinate that planning? So at a high level, the run stage means the tighter traditional feedback loops. So some of that is already happening. You have generation planners that are optimizing the optimal expansion of bulk assets and the optimal operation of those generation and storage assets, and sending those dispatch conditions to the transmission counterpart. I've heard many times transmission planners tell me the resource planner throws me their data over the wall, which means there is no feedback. The data is thrown, they receive it, they feed it in, and the integration often ends there for many reasons that I'm not gonna go into the details. But this run integrated planning workflow phase is meant to unpack that and provide more feedback in that process. So you're gonna have your generation planners that determine active power dispatches that are optimal for your system. You're gonna have transmission planners that are going to determine potential physical violations and constraints. But then this allows a feedback loop to adapt or define new, we call them here mitigation strategies. What we mean here is either operational constraints or capacity investments in infrastructure, in new generation and storage assets, and so on. So as we dig deeper into this workflow, a generation planner will run a production cost model, will define time series of active power for all generators, and provides that to the transmission planner, which can then run power flow simulations to check for violation periods. Is that optimal dispatch scenario feasible? If it's not, here there is an opportunity for already an intermediate feedback loop to adapt the configuration of the system, either in terms of operational constraints or in terms of capacity investments. If there are no violations, now you can go into a reliability screening. So you can run, for instance, contingency analysis that traditionally you will run for peak demand periods. Here we've added what we call a heuristic filter, which means, do you want to run a contingency analysis for every hour of the year, or do you want to do that for a subset of periods that meet a certain security criteria? And then if you have no reliability violation periods, then you can compare the mitigation strategies in terms of cost and reliability impacts. And the guidebook provides actually a cost comparison test to provide practical ways of how you can compare these mitigation strategies. If the changes that are required are major, you may actually want to pass back that to the resource planning. You may want to rerun your capacity expansion models to reevaluate. If the changes are minimal, you can assume you have arrived at an integrated generation and transmission planning solution that meets the economic and reliability needs of the system. And I could go into much more detail here, but you'll be able to get to much more detail on this in the guidebook. I just want to finish very quickly with 3 more slides. This walk, jog, run stage is applied across all these 5 different interfaces. So the level of detail that I just described across generation and transmission is also available in the guidebook between these other interfaces. The guidebook discusses the value of integrated planning across these different phases, across the different interconnections in terms of lowering cost, increasing resilience, streamlining processes, providing data integrity, providing synergistic outcomes, and balancing competing objectives. And it includes examples from industry spotlights where some of this value has already been experienced through integrated planning processes. And finally, I want to just mention that integrated planning is clearly very complex, as I've just described, as Aaron has just described, but there is a lot of technologies that are being developed and are being put in practice that can help with the practical process of doing integrated planning. That includes working with spatially referenced data, the ability of a transmission and distribution planners to map their data against one another. Interoperability across modeling domains, the ability to actually interface production cost models with power flow simulations like I showed, either through, for example, a middleware that can connect different tools or an integrated planning tool. High dimension data processing, tools that can help through statistical processes and machine learning processes to transform large amounts of data outputs into meaningful insights. Computational performance improvements. Integrated planning requires a large and many simulations, the ability to do that in a tractable manner, and ultimately a single point of interaction user experience. I've heard many utilities say one of the challenges with integrated planning is I need to figure out a way to interconnect 5 different tools that were not developed to talk to one another. And there are solutions that integrate these tools or integrated solution. And I want to say that this is really, it's very close to my heart, because this is what we work on at encoord on a daily basis with the team as we deploy our integrated planning solution and as we work with utilities and system operators to understand how can we develop solutions that can really help them integrate planning processes in an easy way. And with that, I conclude. I hope you can all take a look at the integrated planning guidebook that is going to be published in the summer. And I want to end by thanking again ISIC and the task force members for the fantastic input and invaluable feedback you've been providing since we started working on this. Thank you.
So, good afternoon. It's now my challenge to present to you within 15 minutes a pan-European system development product, which which takes 2 years to be conducted and is executed twice biannually. Myself, I'm from Amprion, which is a German TSO, but I'm speaking here today on behalf of NCE, which is the European Association of Transmission System Operators. A few figures here about NCE, just to mention, it was really important that association covers the entire Europe by its members, 40 TSOs from 36 countries, but the legal mandate NCE has only cover the 27 countries of the European Union, which are represented by 31 of the 40 TSOs here in Europe. Typically, it's 1 TSO per country, with the exception for Austria, which has 2, and the exception for Germany, which has 4 TSOs. The 10 years network development plan is one of the 3 legal mandates in the system development domain of NCE, where we have from the bottom to the top, the seasonal outlook, which gives a prospect of the resource adequacy for the next winter and summer periods. It's published twice a year. And then we have on the midterm horizon, 2 to 10 years, the European resource adequacy assessment to assess adequacy concern within that time horizon. And on the long term, we have the system development plan. It covers target years. Well, the title is 10 years, but it addresses a horizon from 10 to 30 years. And the objective of that plan is to develop the European transmission system, which is needed to achieve the European Union energy policy and climate targets, and to materialize the socio-economic welfare from the completion of the European internal electricity market. The process of the TONDP is rather straightforward. First step is to develop energy scenarios. Based on the scenarios, we then identified what are the system needs. So where do we need infrastructure in the electricity transmission system? Next step is then to assess and collect projects from project promoters. Also important, the TONDP, our answer itself, does not develop or identify any kind of project. We simply collect them from project promoters. Project promoters are typically the TSOs across Europe, but we also have some third-party promoters, for example, for developing DC merchant lines, for example. For all these projects, then a cost-benefit analysis is done, and the final step is that for all these projects which have a positive outcome on the assessment, they are eligible then to the European list of projects of common interest or mutual interest, for which some kind of project promoters are really keen to get on that list, because those projects in that European list, they have some kind of priority in terms of easier or reduced permitting processes, and you have an option of financial funding from the EU for such kind of projects. So let's start with the scenarios, and now with the scenarios, I come to integrated planning. And from the previous presentation, I have now learned that we obviously have a different definition of integrated planning in Europe than we have here, where it's a rather kind of vertically integrated planning. With integrated scenarios in Europe, we consider the development of energy scenario across sectors. And in particular here, the scenario framework for our electricity 10 years network development plan is developed together with the gas and hydrogen sector, where we have our counterpart, the ENSOG European Association. Both have to do their own development plans, but these development plans shall be based on common scenarios. So we develop them together, and that is what we call integrated planning in this context. The opposite, or the other part, is coordinated planning, to which I will come at a later chart here. Scenarios where we develop have in common that they shall meet the European energy and policy targets. And typically we have 3 scenarios which we investigate in these different stages of the TONDP process. Not every scenario is used for every study, but it's kind of a mix. And the 3 scenarios we use is typically, one is to develop bottom up. It is called the national trend scenario. It is based on the national energy and policy and target, energy and climate policy targets, which are then consolidated and validated across the European-wide targets, because typically it's not that easy that you simply have to sum up all national targets and achieve the European targets. Then you have to do some consolidation efforts still. And the other 2 scenarios which we typically develop are the so-called distributed energy and global ambition scenarios. These are developed top-down. So by starting with the pan-European targets and then showing different paths towards achieving them. So different distribution of the single scenario parameters to the member states. Based on the scenarios, then the system needs are identified, and system needs identification is typically done then by, and that is now sector specific. Now we talk about only the electricity sector, where we have based on investment modeling, we identify which expansion needs do we see in Europe. And it's important to mention the granularity of this study. Typically, The granularity of the TYNDP is the market bidding zone level. Typically, a market bidding zone equals to a member state or a country's territory. In most cases, some countries have more than one bidding zone. And the objective of this TYNDP is to identify the needs for transmission infrastructure expansion between the bidding zones. So it's typically about cross-border projects. We're not developing the entire transmission system at national level here, but have a strong focus on the cross-border expansion only. So based on the scenarios, we do this investment modeling, and then that is a very rough sketch of the model applied. And that stage we call coordinated planning, because now we separate to some extent between the different energy sectors, which means that we model other sectors, for example, gas and hydrogen as well, but it is not a co-optimization of both. We have rather identified before and when developing the scenarios, the interfaces, and with gas and hydrogen, interfaces are typically electrolyzers or gas or hydrogen fired power plants. These are then fixed, and then we run the investment model based on these conditions for the electricity sector. To give you an overview on what system needs have we identified in these this year's or this 2024 cycle of the TYNDP, and it is focused on the electricity infrastructure. Investment candidates in this context are transmission lines, energy storage options, and when it comes to offshore, we have an offshore part in particular for the North Sea, where we have as investment candidates so-called hybrid solution, which is a connection of offshore wind generation to interconnectors between the adjacent countries at the North Sea. All other kind of infrastructure solutions are considered as well, but already in the scenario building stage. So that is, for example, any kind of this demand flexibility or smart grids. The effects of them you typically find in the load profiles or also in the relevant generation portfolios. So typical results, I will show now for the results for 2 of the 3 target years. So 3 target years, I forgot to mention, of the 2024 TYNDP were 2030, 40, and 50. And in 2030, which is only 5 years ahead, we already see that on top of the 160 gigawatt cross-border capacity, so cross-border transmission capacity between bidding zones, where we expect to have 160 gigawatts in 2030, additional 88 gigawatts would provide additional benefits to the European society, and also 65 gigawatt of further storage facilities. In terms of costs and benefits, it's said that when we invest up to 2030, 5 billion euros per year, it would result in a societal benefit of system costs of 8 billion euros per year. So the net effect is 5 billion euros. This is a map which displays where you find the transmission system needs in 2030. The darker and thicker the line, the more capacity is needed, and you see a certain focus that most expansion or centers of expansion are in Scandinavia, connecting you to continental Europe and all around Germany. Similar figures here for 2040, sorry. There, compared to the 2030 reference, it shows that 108 gigawatts of additional cross-border capacity would be of societal benefit. And here, for the first time, it comes, the offshore infrastructure in the North Sea mainly comes in. The study concludes that 20 gigawatts of offshore hybrid corridors in the North Sea would be beneficial as well. And the storage number is 227 gigawatts. In terms of costs and savings, we see that every euro invested until 2020 returns into €2 saved in system costs. So we have investments, 6 billion euros per year, and a socio-economic welfare of 13 billion euro, a bit more than two ratio of 1 to 2. Here again, a map displaying the system needs. It is a bit similar to what we have seen for 2030 already, but even more than, and in particular for the North Sea region, you recognize that there's a significant infrastructure to be developed until then, or would be beneficial if it was developed until then for socio-economic welfare. The system needs study also when comparing with the projects available show that the system needs go far beyond on what is available by projects so far. That is also then an invite, of course, for any potential project promoters to develop further projects. The thicker the dots are between the borders here, the more transmission capacity would create further socioeconomic benefits. And typically that is also the link to the next cycle, because based on the system needs, which are not covered yet by project promoters are invited to submit to NCE for the next cycle further projects that we then can assess for their benefits to the European society. Here again, a couple of figures, which I may not go to in detail, but it shows that within the different objectives we have benefits in socioeconomic welfare, in security of supply, in RES integration, CO2 emission reduction, and so on. So all the relevant aspects to be addressed by transmission system development are investigated and show certain benefits. Just a brief outlook on the volume of projects we have assessed in the cycle. We have a total of 170 transmission project candidates, which equal to 348 investments in different grid infrastructure, maybe transmission lines or substation and so on, that form the infrastructure portfolio. And we had a portfolio of 33 storage project candidates which were assessed. The cost-benefit analysis is then done based on a reference grid for each target year. We either add an additional project and calculate the difference of the system costs, or in case a project is already part of the reference grid, we take it out from the reference grid and again calculate the difference in system costs with and without the project, and that is how we conclude on the socio-economic welfare of each project. But that is only one indicator of the entire study. It's B1, it's a socio-economic welfare. We have a similar approach, always taking in or taking out a single project, where you then also calculate the impact on the CO2 emissions, impact on RES integrations, grid losses, system adequacy studies are done, system security analysis is done. Many of that at pan-European level with a common methodology for all projects, but some of these indicators are less mature. They are rather project-specific. We call them project-level indicators, so they are then calculated, investigated by each project promoter itself and not by NCE in total. And it is also not necessary to investigate each of the indicators for every project. A selection may be sufficient by each, speaking in other words, by each, let's say, indicator you identify benefit, you could collect certain points, and if you have enough points, then you become eligible to the project European list for the projects of common interest or mutual interest. Also, an interesting figure is about the volume of analysis we do here in market network studies, supply security of supply studies, and so on, which means that in total, we investigate around 500 million points in time of the European system in future. And that is quite, let's say, impressive number, I guess, also to show how extensive this exercise is, and it actually requires the engagement of all the German TSOs who provide the computational resources towards NCE, supported in a large number of project teams, project groups to do this extensive assessment. So we had to conclude my presentations, we have three main findings from the 2024 exercise. As already said, we see a huge socio-economic welfare in Europe for further expanding the transmission system. By 2040, each euro invested in return delivers 2 euros saved in system costs. We see a huge benefit also way forward for to achieve the energy policy and climate targets by displacing the fossil-based generation and increasing the RES integration. And third main finding was what we already have now in our project portfolio only covers a part of these needs. So again, that is a call for project promoters to develop further projects to be submitted to NCE to be considered then in the next exercise of the 10 years network development plan. And the documentations about the scenarios, the needs studies, and so on, you will find on the relevant website there. And if you're interested, you can study everything there extensively. Thank you very much.